Alright class, so hopefully you watched the first video which explained a little bit about variational theory and went through the steps. In this video we're going to work through an example problem. And really with variational and perturbation theory, it's going to be important that you work through some example problems. This is what I would have had you do in class. You would have worked through an example problem together, and then I would have broken you up into teams and had you work through, or at least work through setting up another example problem. Because the more of these you do, the more it's going to make sense. So the problem that we'll look at today is let's use variational theory to approximate the ground state energy of a harmonic oscillator. So this is a nice system to start with for variational theory because we actually already know what the right answer is. So we're going to choose a guess function that isn't our real harmonic oscillator function, but that has the right bounds and is somewhat reasonable, and we're going to see if we can actually get the right answer or close to the right answer using variational theory. So our trial function that we're going to choose is phi of x is equal to the exponential function of negative c x squared, where our variational parameter is c. So note that our ground state wave function for harmonic oscillator does have an exponential that is some negative constant x squared within it. So this should have the right bounds. And if we think about the bounds for harmonic oscillator, we know that as x goes to negative infinity and as x goes to infinity, the wave function should go to 0, which it does. Remember, the wave function goes to 0 at those bounds. As we go towards, or I guess not at those bounds, more like at those limits, because these aren't firm bounds, they're limits. And we can see that our trial function, if we were to think about the limit of our trial function, as it goes to negative infinity or x goes to infinity, we will also get 0 at both of those limits. So this is a reasonable trial function. So let's move forward. So let's determine E phi. And so our Hamiltonian, because this is variational theory, we're going to use our Hamiltonian for our closest known model system. And of course our closest known model system is in fact still the harmonic oscillator. So we'll use that h hat is equal to negative h bar squared over 2 mu, second derivative with respect to x, plus k over 2x squared as our operator. And that's coming directly from harmonic oscillator. And so if we apply our Hamiltonian to our trial wave function, we'll get the following expression. So here we just have, I've taken one derivative, but I haven't taken the second derivative yet. And here we just have the v of x term times the wave function, which in this case is phi, right? All right, so let's go ahead and take the second derivative and finish expressing that. So when we take the second derivative, now we've got to use the product rule because we have an x function times an x function when we take our second derivative. So we should get something along the lines of h bar squared c over mu all times the exponential function minus cx squared minus 2cx squared, the exponential function e to the minus cx squared, plus k over 2 x squared e to the minus cx squared. Okay. So we've applied the Hamiltonian to phi. Now we need to multiply that result by phi star and take the integral from negative infinity to infinity with respect to x. And so if we plug all of that in, we're going to get all of our exponential functions are going to become e to the minus 2c x squared when we multiply by phi star. And if we notice, both of these functions, e to the negative 2cx squared and x squared e to the negative 2cx squared, are both even functions. Remember that an even function means when we're integrating from negative infinity to infinity means we can change our bounds, multiply the integral by 2, and change the bounds from 0 to infinity. And many of these are definite integrals that we can look up in our integral table. So let's go ahead and make that change, and we're going to pull all our constants out front, and I'm actually going to separate this into two integrals. And so we've pulled out the 2, we've changed the bounds for both of our integrals. Now we need to know what those integrals are. So the integral e to the minus 2cx squared dx is 1/2 pi over 2c to the 1/2. And the integral of x squared e to the minus 2cx squared from 0 to infinity is 1 over 8c square root of pi over 2c. So let's plug those in. So we'll have our constant 2h bar squared c over mu times 1/2 pi over 2c square root plus 2 times the quantity k over 2 minus 2 h bar squared c squared over mu times 1 over 8c square root of pi over 2c, which we can simplify that a little bit and combine some terms. And we're going to leave this square root of pi over 2c out because I know things that you don't yet. We haven't done our second integral. Remember that this integral is only the numerator when we're trying to figure out the energy. So we need to figure out the denominator. So let's go ahead and do that. So the denominator is going to be the integral from negative infinity to positive infinity of phi star phi. So that's just going to be the integral from negative infinity to infinity of e to the minus 2cx squared, which we already said is even. So we can pull out a 2 and change our bounds from 0 to infinity. And in fact, we already have that integral. It's the one in green to the right. So we already know what that integral is. So we can go ahead and plug all of that in. And we're just going to end up with square root of pi over 2c. So now you see maybe why I left this out over here. Okay. So the energy with respect to phi is this integral result divided by this integral result. So let's do that, and we're just going to write these constants back. And so we're going to get h bar squared c over mu plus k over 8c minus h bar squared c over 2 mu, which we can simplify and combine to get h bar squared c over 2 mu plus k over 8c. And so we're getting some function or expression for energy that still depends on our variational parameter c. So what do we do with that? So the next step, step 3 in variational theory, is that we need to minimize our energy expression. And the way we're going to do that is we're going to take the first derivative with respect to our variational parameter c, and then we're going to set that equal to 0. So let's minimize by taking this integral. Sorry, I have some math errors here. All right, so the first derivative of our energy function should go to h bar squared over 2 mu minus k over hc squared. And we're going to set that equal to 0 and solve for c, right? Solve for c at that minimum. And so we can rearrange this to be k over 8c squared equals h bar squared over 2 mu. And then we can continue to rearrange that to get that c is equal to 1 over 2 h bar square root of k times mu. So this is our minimal c. When c is equal to this, we should have our minimized or optimized energy. So we're going to plug this value of c back in to our energy expression, which was up here. All right, so we're going to get that the energy of phi is h bar squared over 2 mu, 1 over 2 h bar, square root of k mu, plus k over 8, 2h bar divided by the square root of k mu, because here we had a 1 over c term. And so if we simplify this, we get h bar over 2 times the square root of k over mu. Does that look familiar by chance? So scroll back in your notes, pause the video for a minute, scroll back in your notes, and look at what the ground state energy of a harmonic oscillator is. So what is the real ground state energy for a harmonic oscillator? So our expression is h sub nu equals h bar square root of k over mu times quantum number nu plus 1/2, and the ground state quantum number is nu equals 0, which gives us back exactly what we got up here, right? That energy is equal to h bar over 2 square root of k over mu. So we can see here that variational theory does work. Granted, this was a simple system that we already knew the right answer to, and you can imagine that as we get to more complex systems, our chances of being very incorrect in choosing our trial wave function are going to increase exponentially. And so do keep that in mind, that variational theory is only as good as your initial guess at a wave function. So your trial wave function guess here is incredibly important. Okay, so now I'm posting a reading and some practice problems on the Moodle page. I would strongly recommend that you go ahead and work through those. I will also post solutions, full solutions to those problems before you move on to perturbation theory.